Bismillahirrahmanirrahim. Hello and welcome to lecture number 3 of the course of Differential Geometry. Lecture number 2 में हमने वेक्टर की डेफिनेशन से स्टार्ट लिया था, उसके बाद हमने टेंजेंट स्पेस की डेफिनेशन की, उसके बाद हमने वेक्टर फील्ड्स को डिफाइन किया और उसके बाद हमने देखा कि हाउ वी कैन राइट डाउन ए वेक्टर फील्ड इनटू सिंपलर वेक्टर फील्ड्स which are natural frame field on R3. And we also did some questions from exercise. इस lecture में we will be interested in directional derivatives. What does directional derivative mean in R3? And how we can compute them more efficiently. And for that we need to revise or recall what is the chain rule to differentiate composite functions. And then we will end up this section with the main properties of the directional derivatives, which will obviously help you to calculate directional derivatives. And the last section would be operation of a vector field. And then we'll calculate and we will see the basic properties of operations of vector fields. And once again we will see that how these properties can help us to do the calculations. So one might ask, why directional derivatives? Because they have many applications in almost every area of science. So for example, in computer science, image recognition, once you have an image in your computer, how you can optimize the image, how you can improve the image to see what actually it is. So for example, in this case, if you have an image like this, initial image, which is very fade, which is not very clear, then you can apply this technique of directional derivatives to improve the image. And this is one of the use of directional derivatives. There are many other uses of directional derivatives. So to start with the definition of directional derivative, we need to first see the equation of a line associated to a tangent vector. So for example, if you have a point and you have a vector with the P as initial point, so it clearly means that this vector V is part of the tangent space at that point P. So there is a line associated to this, which is the line containing this vector. So for example, if you have point P equals 1, 1, 1, and if you have a vector equals, let's say 2, 3, 4, then the line associated to this vector whose initial point is P is given as T goes to 1, 1, 1 plus T into V, which is 2, 3, 4. So which is equal to 1 plus 2T, 1 plus 3T, and 1 plus 4T. So T goes to 1 plus 2T, 1 plus 3T, and 1 plus 4T. So what does these coefficients or coordinates means? So this means that if I take any particular value of T, let's say T is equal to 0, then it will give me 1, 1, and 1, and which we know that it's a point on the line. So the line containing this vector contains this point. And similarly, if I take T is equal to 1, then I will get 3, 4, and 5, which is going to be another point on the same line, 3, 4, 5, up to so on. So for every value of t, it's going to give me a point on the line. So these are the parametric equations of line. So in short, given any tangent vector at a point in R3, there will be a line associated to that tangent vector at point P. Now we are going to use this line to define the directional derivative. So given any function f, we can draw its graph. It's going to be a surface in R3, and on surface there are many curves. So for example, passing through point P, there are many curves. But we choose one direction. So the direction which is associated to this vector VP, because corresponding to VP there is a line, and corresponding to this line there is going to be a curve on the surface, and directional derivative of any function f in this direction, in the line direction, would mean that you are actually differentiating this curve in the same way that you did in calculus of one variables. So this is a curve, you can easily differentiate it. So this f of p plus tb, it's a function of one variable, and the variable is t, and you know how to differentiate functions of one variables. And then at t is equal to 0, because t is equal to 0 corresponds to the point P. So this point P corresponds to the value t is equal to 0. So what is directional derivative then? Given any function f, you can sketch its graph in R3. It's going to be a surface in R3, and then you choose a direction given by this vector VP, which is a vector with initial point P in the direction of vector V, and there is a line corresponding to VP, and then there is a curve corresponding to this line on the surface, and then directional derivative at point P in this direction of line means you are actually differentiating this curve at this point P, and this is the same derivative as we used to do in calculus of one variables. So basically, what is directional derivative of a function associated to this vector VP? It's basically the rate of change of functions, this curve. So the number VP of f is called the derivative of f with respect to VP. And we also say that VP of f is a directional derivative. The directional derivative VP of f informs us about the change in the value of f as we move away from P in the direction VP. So once again, we are moving in the direction of VP along the line that VP defines. So in other words, we are calculating the rate of change along this curve. So it's the same case as we used to do in calculus. So given any curve, we can calculate the rate of change at any point, and it was slope of the tangent line at that point. So how to compute the directional derivative VP of f? So consider a function f is equal to x square yz, and the point P to be 1, 1, 0, and the vector V to be 1, 0, 3. So first we compute P plus TV. What is P plus TV? P is 1, 1, 0, and V is 1, 0, minus 3, and multiplied by T. How do we add two vectors, we just add their corresponding components. So we will get 1 plus t, and then 1 plus 0t is 1, 0 plus minus 3t is minus 3t. So this is basically the line associated to VP. Now evaluating f along the line, and why we are evaluating it, let's go back one slide. We are evaluating it because we need f of p plus t according to the definition of the directional derivative. Okay, so we calculated f of p plus tb. What is p plus tb? It's 1 plus t, 1 minus 3t. So it means f of 1 plus t, 1 minus 3t. So the x coordinate is 1 plus t, y coordinate is 1, z coordinate is minus 3t. So what is f of 1 plus t, 1 minus 3t? It's just x square yz, but we replace x with the x coordinate, which is 1 plus t. So 1 plus t square, and we replace y with the y coordinate, which is 1, and we replace z with the z coordinate, which is minus 3t, and we get minus 3t plus minus 6t square minus 3t cube. Now once again, according to the definition, we need to calculate d by dt of f of p plus tb. And what is d by dt of f of p plus tb? It's the same as d by dt of minus 3t minus 6t square minus 3t cube, because we just calculated that what is f of p plus tb. It's just minus 3t minus 6t square minus 3t cube. So this is equal to, it's just the derivative of this polynomial in t, and we are taking the derivative of this polynomial with respect to t. So what is the derivative of minus 3t? It's just minus 3. And what is the derivative of minus 6t square? It's minus 12t, and derivative of minus 3t cube is minus 9t square. And the last step to calculate the directional derivative of f in the direction of VP is to put t is equal to 0 in this expression, which is d by dt of f of p plus tv. So we are going to put t is equal to 0 in this expression we just calculated, and this term becomes 0, this term becomes 0, and we are left with the number minus 3. So VP of f in this case is a number. Now we want to simplify this method of calculating directional derivative of a function in a given direction. And to simplify the situation, we need to first recall what does a chain rule mean. So chain rule for a function f, which is function from r cube to r, it's a real valued function, such that there exist three real valued functions, a, b and c, defined as t goes to a of t, b is defined as t goes to b of t, and c is defined as t goes to c of t, and these are all differentiable functions of one variables. Then the function f of a, b, c, which is again a function from r to r, defined as t goes to f of a of t, b of t, c of t. Then d by dt of f of a, b, c. Now we are using d and not partial because it's a function of one variable now. It's the same thing as we have seen in the previous example, that f over here is a function from r3 to r, defined as x square yz. But when you evaluate this on these functions of one variable, which are t, 1 plus t, 1 and minus 3t, then you get function of one variable, and the variable is t. So similarly, this function f of a, b, c is a function of one variable, and to calculate the rate of change of f with respect to t, we can use this rule called the chain rule. So for example, if you have f defined as x square y z, and you have a from R to R defined as a of t goes to, let's say, t plus 1, and you have b from R to R defined as b of t is equal to, let's say, t square, and you have c from R to R defined as c of t is equal to, let's say, t cube. Then what is f of a, b and c? It's the same as f of 1 plus t, t square and t cube, which is the same as 1 plus t square, t square and t cube, which is going to be equal to t raised to power 5 1 plus t square. So if you want to calculate what is d by dt of this f, which you can in fact calculate it directly, but you can also use the chain rule. So this chain rule is useful when you have complex kind of a, b and c functions, or they are implicit functions. But in this case you can directly calculate what is d by dt of f of a, b and c. So what is this? We can use the product rule, t raised to power 5 multiplied by 2 into 1 plus t plus 1 plus t 5 into t raised to power 4. So we can also use the chain rule to calculate d by dt of f of a, b, c. So in this case we have f equal to x square y z, and f of a, b, c equals to 1 plus t square, t square and t cube. So what is partial f by partial x? In this case, when you are calculating the partial derivatives of a function, so for example in this case when you are calculating partial derivative of f with respect to x, then you are keeping the rest of the variables as constants, so they will behave like constants. So it becomes 2x and yz remains the same because we are treating them like constants. And similarly, what is partial f by partial y? X square and z remains the same because we are treating them like constants, and the derivative of y with respect to y is 1. And similarly, what is partial f by partial z? It's basically x square and z. Now according to the formula, what's the next thing we need to calculate? We need to calculate dA by dt, dB by dt and dC by dt. So what is dA by dt? It's basically 2 into 1 plus t. What is dB by dt? It's basically 2t. And what is dC by dt? Is basically 3t square. Now according to the formula, what is dF by dt? It's basically partial f by partial x at ABC multiplied by dA by dt plus partial f by partial y at ABC multiplied by dB by dt plus partial f by partial z at ABC multiplied by dC by dt. We have calculated partial f by partial x, but what's its value at point ABC? It's basically 2 into 1 plus t square and t cube multiplied by dA by dt, which is going to be 2 into 1 plus t, plus what is partial f by partial y at point ABC? It's basically x square 1 plus t square and then square z, which is basically c, which is t cube, multiplied by dB by dt, which is just 2t, plus partial f by partial z, which is x square y. And so it becomes 1 plus t square whole t square and t square multiplied by dc by dt, which is 3t square. Now if we simplify this thing, then we'll get exactly the same answer as we get by directly evaluating it. So this is the chain rule. Now we are going to use the chain rule. I am leaving this as an exercise. You can see yourself that they are equal. So we can use this chain rule to prove the following lemma, which will help us to simplify our calculation when we are calculating the directional derivative. So if v, p, is a vector, and this vector means that the initial point of the vector is p, and the vector form is given as v1, v2, v3, is a tangent vector to R3, then the directional derivative of f in the direction of vp is basically the summation v1 partial f by partial x1 of p plus v2 partial x by, so let me write it in a form which does not involve the summation partial f by partial x2 at point P plus v3 partial f by partial x3 of P. So sometimes we use x, y, z, and sometimes we use x1, x2, x3, but they are just the names of the variables. So x1 corresponds to the x variable, the first coefficient, x2 corresponds to the second variable, the y variable, and x3 corresponds to the z variable or the third variable. So let's have a look at the proof of the lemma, how we can say that the directional derivative of f in the direction of vp is just this expression. So we know that what is p plus tv, this is just p1 plus tv1 plus p2 plus tv2 and p3 plus tv3, where p1, p2, p3 are coefficients of this vector, of this point. So now what is f of p plus tv? It's just f of the same expression we just calculated. And in order to use the chain rule, we need these expressions d by dt of pi plus tvi, and by definition this is just this. So this means that in fact what is d by dt of p1, which is just a number, plus t v1, and this number v1 is the first coefficient of the vector. So this is going to be equal to the derivative of p1 with respect to t is 0, because p1 is just a number, is a fixed number, it's the first coordinate of p. So this is 0 plus v1, once again a number, it will come out when you are taking the derivative, and the derivative of t with respect to t is 1, so this is just v1. And similarly we can calculate for other, and in general we can just say that d by dt of pi plus tvi is equal to vi. Now by definition, what is the directional derivative of f in the direction of vp? It is just equal to this expression. Now we also know that how can I differentiate a function which is function of one variable indirectly, but directly it's a function of three variables, and then every of them is a function of one variable. So we can use chain rule over here. So what is chain rule? Partial f by partial x1 d by dt of p1 plus tv1, because p1 plus tv1 is a in this case. So this number is a in this case, this number is b in this case, and this number is c in this case. And so by chain rule, this is just partial f by partial x1 d by dt of p1 plus tv1 plus partial f by partial x2 d by dt of p1 plus tv2 and plus partial f by partial x3 d by dt of p3 plus tv3. So this is just equal to this. Now we have calculated that d by dt of pi plus tvi is vi, so we can just replace this value over here. It will become vi, and at t is equal to 0, pi plus tvi is just the point p. So we are basically calculating partial f by partial xi at point p. So from now onwards, we can simplify the calculation of directional derivative using this expression, which we proved by this lemma. So let's compute the directional derivative of the same example which we did before the lemma. So we have the same function x square yz, and we have the same point 1 1 0, and we have the same vector 1 0 minus 3. So according to this formula, we need to know what is partial f by partial x, and in this case it's 2x yz, because we are keeping y and z, or we are treating y and z as constants, and the derivative of x square with respect to x is 2x. So it becomes 2x yz. And similarly, what is partial f by partial y? We are taking derivative of f with respect to y, and we are keeping x and y terms as constants. So it becomes x square z. And similarly, what is partial f by partial z? It is x square y, because we treated x and y as constants, and the derivative of z with respect to z is 1. And now we want to calculate the values of partial derivatives at point P. According to the formula, we need to calculate the values partial f by partial xi's, or in this case partial f by partial x, partial f by partial y, and partial f by partial z at point P. And what is point P in this case? It's 1 1 0. So we need to calculate the value of this partial derivative at point 1 1 0. So which means we will replace x with 1, y with 1, and z with 0. So if we replace x with 1, y with 1, and z with 0, then we will get 0, because z is 0 and the rest of them will become 0. Similarly, what is partial f by partial y? It's basically x square z, so we will replace x with 1 and z with 0. So it will become 0 again, because z is 0. And what is partial f by partial z? Which is x square y, and at point P we will replace x with 1 and y with 1, and so it become 1. So putting all of these values in our formula, we will get this. So explicitly, in a more explicit form, this formula is just v1 partial f by partial x at point 1 1 0 plus v2 partial f by partial y at point 1 1 0 plus v3 partial f by partial z at point 1 1 0. And what is partial f by partial x? It's 0, which is here. What is partial f by partial y? It's once again 0, it's written over here. What is partial f by partial z? It's 1, which is written over here. What is the coefficient? So the first coefficient of v in this case is given to be 1. so which is over here. This is basically v1, and the second coefficient is 0, which is over here, and the third coefficient is v3, which is -3, which is over here. And if we sum them, we will get -3. And if you remember that when we calculated the directional derivative by definition without using the lemma, it was difficult, and we also remember the answer was -3, which is the same as we calculated by using the lemma. So the answer is same, the directional derivative is same, but the process has been simplified. अब हम आसानी से calculate कर सकते हैं directional derivative using this lemma. Now we see some properties of directional derivatives which will help us to calculate directional derivatives more efficiently. ज़्यादा आसानी के साथ हम calculate कर लेंगे directional derivative को अगर हम इन properties को apply करें. So the first part says that AVP plus BWP, the directional derivative of f in this direction is the same as AVP of f plus b multiplied by the directional derivative of f in the direction of WP. So we know that this is equal to AV plus BW at point P at f. So this is equal to, so let V is given as the components V1, V2, V3, and W is given as W1, W2, and W3. Then for scalars A and B, AV plus BW is given as AV1 plus BW1, AV2 plus BW2, and AV3 plus BW3. So by definition, by using the lemma which we just proved, that the directional derivative of f in the direction of P is just the components V1, V2, V3 multiplied by partial f by partial xi at point P. So by using that, what is directional derivative of f in the direction of AV plus BW? It's basically equal to AV1 plus BW1 multiplied by partial f by partial x at point P plus AV2 plus BW2 multiplied by partial f by partial y at point P plus AV3 plus BW3 multiplied by partial f by partial z at point P. Now we can simplify and we can say that this is equal to A into V1 partial f by partial x at P plus V2 partial f by partial x, y at P plus V3 partial f by partial z at P plus B into W1 partial f by partial x at P plus W2 partial f by partial y at P plus W3 partial f by partial z at point P, and which is exactly equal to A partial derivative of f in the direction of Vp plus B into the partial derivative of Wp partial derivative of f in the direction of Wp. So this was the first part of the proof. The second part can be done similarly. So this was the proof of the first part of the statement, and to prove the second part, it's very simple, and I'm leaving it as an exercise. So to prove the third part, we see that let V be given in the component form as V1, V2, V3, then we can write down according to the lemma which we just proved, that the directional derivative of Fg in the direction of Vp is the same as V1 partial Fg by partial x1 at point P plus V2 partial Fg by partial x2 at P plus V3 partial Fg by partial x3 at point P. But according to the product rule, we can say that partial Fg by partial xi is equal to partial F by partial xi multiplied by g plus F multiplied by partial g by partial xi. So by using this expression, we can easily see that the directional derivative of Fg in the direction of Vp is equal to, so we just replace this expression in place of partial Fg by partial xi, and it becomes this, so which is exactly equal to, so we can take this g of p common because it's present in each and every term. So this is equal to the summation Vi partial F by partial xi at point P and multiplied by g of p plus f of p, which is once again common in each and every term, is multiplied by summation Vi partial g by partial xi at point P, which is equal to, so this expression once again according to the lemma which we proved, that this expression is basically the directional derivative of f in the direction of Vp, and this expression over here is basically the directional derivative of g in the direction of Vp. So we have proved the third part and the last part of the theorem. Now the last section of our today's lecture is operation of a vector field. Now we know that vector field is a function that assigns to every point in space a vector. So we can operate this vector field on a function. So in other words, if we operate this vector field on a function, we will get a function, and this function is defined as, if we calculate the image of this function at any point of the space, it's the same as calculating the directional derivative of f at v of p, or the directional derivative of f in the direction of v of p. So remember, v of p is a vector whose point of application is p, and it's some vector. So we are calculating the directional derivative of f in the direction of v of p. So that's how you apply a vector field on a function, which is a function from R3 to R. So let's start calculating the operation of a vector field for simple vector fields. So we have seen in our lecture number 2 that there are 3 simple vector fields, and we collectively name them as natural frame field, u1, u2 and u3, and we define them as u1 of p is basically 1, 0, 0 at point P. So it's just a unit vector in the direction of x-axis, and the initial point or the point of application of the vector is point P. So what is u1 of f? It's a function, and what are the images of this function? So let's calculate the image of this function u1 of f at point P. So this is just equal to u1 of p at f. In other words, the directional derivative of f in the direction of u1 of p. So by using the lemma, we can simplify calculating the directional derivative of f in the direction of u1 of p, and this gives us 1, 1, 0 at p of f, which means the directional derivative of f in the direction of 1, 1, 0 at point P. So by using this lemma, this must be equal to v1 partial f by partial x1 at point P plus v2 partial f by partial x2 at P plus v3 partial f by partial x3 at point P. So what is point P in this case? It could be any point of the space. It's not specified. But we know that what are v1, v2 and v3 in this case. So what is v1 in this case? v1 is 1. What is v2 in this case? v2 is 0. What is v3 in this case? v3 is 0 again. So it becomes 1 partial f by partial x at point P plus 0 multiplied by partial f by partial y at point P plus 0 multiplied by partial f by partial z. It should be z at point P, which is equal to partial f by partial x at point P. So the two terms are 0, and at the end we just get the partial derivative of f with respect to x, and we just evaluate that derivative at point P, and you will get u1 of f at that point P. Similarly, if you have the other basic vector field u2, and how do we define u2? u2 of P is equal to 0, 1, 0 at point P. Similarly, you can calculate operation of this vector field on the function f. So at point P, this is just equal to v1 partial f by partial x at point P plus v2 partial f by partial x y at point P plus v3 partial f by partial z at point P. But we also know that what is v1, v2 and v3 in this case, these are just 0, 1, 0 respectively. So what is the value of the operation of a vector field on a function at point P? This is just equal to 0 multiplied by partial f by partial x at point P plus 1 into partial f by partial y at point P plus 0 into partial f by partial z at point P, and this becomes partial f by partial y at point P. And similarly, we can see that operation of the vector field u3 on f at any point P is partial f by partial z at point P, and I am leaving this as an exercise. Now, before going to the exercise, we can have a look at some basic properties of operations of vector fields, which will help us in calculating the directional derivatives and the operation of a vector field on a function, which is again a function. So the first part is, if v and w are any vector fields on R3 and f, g, h are real valued functions, so f, g, h are basically functions from R3 to R. Similarly g and similarly h. Now, when two functions are equal, when do we say that two functions are equal? So remember, in this first statement, it's a function. So this part is a vector field and h is a real valued function, and operation of a vector field on a function is again a function. And similarly, on the right hand side, this v of h is operation of a vector field on a function, and you are multiplying this function with the function f. And similarly, operation of w on h, the real valued function, is again a function, and you are multiplying it with the function g. So both terms are function and their addition is again a function. So left hand side is a function, right hand side is a function, and we want to prove that both functions are equal. So one way of proving that two functions are equal, so let's say f1 and f2 are two functions, then one way to prove that they are equal functions is to prove that their value at each and every point is the same. So if we can prove that the value of both functions at each and every point P of R3 is same, then both functions are equal. So let's start from the left hand side. Fv plus Gw of h at any point P, this is basically equal to, according to the definition of operation of a vector field at any point, it's basically Fv plus Gw operated at P and the whole thing operated at H. So this is equal to Fv of P plus Gw of P applied at H, which is equal to f of P V of P plus G of P W of P applied at H. Now using the above properties, let me recall the proof. Now using the properties that we just proved in another theorem today is A Vp plus B Wp of f is equal to A Vp of f plus B Wp of f. So this is Vp and this f of p is a number because it's a real valued function, so f of p is going to be a number. So I can distribute this on H, so this will become f of p Vp of H plus G of P Wp of H, which is the same as saying that this is the image at point P of the function which is on the right hand side. So the image of this function at any point P is basically the same as the last line which we just proved. So the first part is proved. Similarly, we can see that in order to prove the second part, we use the same strategy. Two functions are equal if and only if their image values at each and every point of the domain are equal. So we have two functions. So the first function is operation of a vector field V on the function which is AF plus BG. So we want to prove that it's the same as A multiplied by the operation of the vector field V on F plus B multiplied by operation of the vector field V on G. So let P be any point in R3, the point of the domain, and operation of the vector field V on AF plus BG of P is equal to V of P AF plus BG, and this is just by definition of the operation of the vector field on a function. And according to this theorem which we just proved, we can say that we can distribute V of P on the values AF plus BG, so it will become A V of P applied on F plus B V of P applied on G. So this is just equal to A V F, so operation of the vector field V on F, because this is just by definition of the operation of the vector field. And similarly plus B operation of V on G at point P, which is equal to A vf plus b vg at point P. So this function and this function have the same functional value at point P, and P is the arbitrary point of R3, and their functional values are equal, which means that the functions are equal. And similarly we can prove the third part, and in third part the hard part is to use this product formula, and I'm leaving this as an exercise. Now let's calculate some examples. If V is a vector field which is given as x square u1 plus y u3, and u1, u2, u3 are once again the natural frame field of R3, and f be a function which is defined as x square y minus y square z, then we need to calculate the operation of the vector field V on f. And by definition, this is just V of f. So by definition of operation of the vector field V on f, this is just equal to the vector field V and the function x square y minus y square z. So by using the property 2, which we just proved, if we are applying a vector field on AF plus BG, it's just equal to A V F plus B V G. So this means that this is equal to the vector field V x square y minus vector field V y square z. And once again, using the first property that we proved, that if you are applying summation of vector fields on H, then it's the same as calculating the operation of vector field V on H multiplied by F plus operation of vector field W on H multiplied by G. So we can write down this as x square u1 of x square y plus y u3 of x square y minus x square u1 of y square z plus multiplied by minus, which becomes minus y u3 of y square z. And now we know that we calculated that the operation of a vector field u1 on any function is just, so operation of any on any function of the vector field u1 is just partial f by partial x. So we just replace this thing by partial x of x square y, which is 2xy. And similarly, what is u3 operated on x square y is the same property for the vector field u3. We proved that it's partial f by partial z. So if we take the partial derivative of x square y with respect to z, then it's 0, because you treat x square y as a constant, there is no z term, so the derivative of a constant is 0. Similarly, u1 of y square z is the partial derivative of y square z with respect to x, and so there is no x term, so the derivative of y square z with respect to x is 0. And similarly, u3 operated on y square z, the partial derivative of y square z with respect to z, which is y square, and so this becomes 2x cube y minus y cube. And similarly, we can do other exercises from the book. Next time we will be interested in curves in R3. So what we have learned in today's lecture? So we have learned what a directional derivative means. In fact, basically we chose a curve on a surface, and then we calculated the derivative at a point of that curve, and it was the same thing as we calculated in calculus of one variables. So we chose a direction and we chose that curve, and then we calculated the derivative of the function, and then we saw some basic properties of the directional derivative, and we see that how they can simplify calculating directional derivatives. And then we saw how we can operate a vector field on a function, and operation of a vector field on a function is again a function. And then we saw some simple properties, and in fact we proved them and we applied them to calculate operation of a vector field on a function. This is the end of the lecture. Thank you very much.